Hello and welcome to section 2.7a, graphs of rational functions. And remember in this section, the examples that I go over, please, if you have any questions on them, please bring them to class and make a mark, write them down, write down what your question is if you don't understand something, so that you can come into class and be like, I need some help with this one. So we're going to graph this function by hand, and it says include at least 5 key points. So we're going to go through and get as many key points as we possibly can. So the first thing that we do with something like this to graph it is I would be looking for either vertical asymptotes, horizontal asymptotes, things like that will help us along our way. And so and then x-intercepts, y-intercepts, and then anything else we can find. So let's start with doing the x-intercepts. So we're going to set this thing equal to 0. So because remember, for x-intercepts, we end up we're finding out we're across the x-axis, so that's where y is 0, so 0 equals 2x minus 1 over x. And so I'm going to solve algebraically. I'm going to multiply both sides by x, which then just gives me 2x minus 1 equals 0, and then if I add 1 across the equal sign, 2x equals 1, and dividing by 2, x equals 1/2. So that means my x-intercept is when I get 1/2 when y is 0. So there's one place that it crosses the x-axis. That's my x-intercept, so I can kind of put a mark there for that one. Then I'm going to go ahead and find the y-intercept. And so y-intercept, so that's when I set the x is equal to 0 and solve for y. And so by doing this, if I say, okay, well, y is really f of x, I'm going to say 2 times 0 minus 1 over 0. And basically what happens is, in this case, with a little quick simplification, y is equal to negative 1 over 0, which basically means there is no y-intercept in the domain, because we can't have the bottom be 0. So we basically don't have a y-intercept in this graph. And so in this case, and partly you'll see when we do this that, well, anyway, there's some good information that we get from this y-intercept when we're looking at it, and we'll kind of talk about it in just a moment here. So then I'm going to look for vertical asymptotes. And vertical asymptotes, remember, are found when we find out that the bottom is equal to 0 of a rational function. So if I set x equal to 0, there is a vertical asymptote. And so that is actually the reason why we didn't have a y-intercept, is that it would have been the x equals 0 line, this green line that I just put in here. The vertical asymptote is not really in the domain, so that's why we don't have a y-intercept. We're not going to ever cross the y-axis. And so we ended up with a vertical asymptote. So then we'll look at horizontal asymptotes. And a horizontal asymptote would actually be, when we look at our function, if you remember from our discussion the other day, horizontal asymptotes are if we have the same power, then we take, in which we do, we have the same degree, x to the 1, x to the 1, we have the same degree, so we take the fraction of the leading coefficients, which happen to be 2 over 1, and set them equal to y, which is really a horizontal asymptote of y equals 2. So I would have a horizontal asymptote at y equals 2 that looks something like this. Alright, so now I know that my graph has to cross the x-axis down here at this blue point. I know it's going to approach both the vertical and the horizontal asymptote. So I know that I could go ahead and pick some points here and try to find out where it's in this function to kind of just get a good idea of what's happening. So I'm going to pick x and y. And since I already have a half here, let's see what x is 1. Let's see when x is 2 what happens. And let's check over on the other side when x is negative 1 and when x is negative 2. And we'll just see what happens with this function. It should give us an idea where our points go. So, well, I know for a fact that my graph is going to be down here because it has to cross the x-axis. But when I plug in 1 into this function, I get 2 minus 1, which is 1 over 1. So at 1, I'm at 1. So I get this point right here. And when I go to 2, I get 4 minus 1, which is 3 over 2, which becomes 3/2. So I have my other point here at 3/2. So you can see that my graph itself will be approaching like this, we'll be approaching that intercept, and it kind of falls off the table, as it approaches that intercept. It's not supposed to cross, it's just supposed to approach it. So then at -1, the reason I'm going to choose -1 is the fact that I want to make sure that I'm on, whether I'm above or below this horizontal asymptote. I could approach the horizontal asymptote this way from underneath, or I could approach it from above. And so that's kind of what I'm checking with the -1, -2. So by plugging in -1 into the function, I get -2 minus 1, which is -3, all over -1, which would be basically 3. So at -1, I'm at +3. I'm up here. And then if I plug in -2, I get -4 minus 1, which is -5 over -2, which becomes 5 over 2, which is 5/2, which means I'm getting closer, which would be about right there. It's just 2.5. So my graph will do something like this. And so as you can see, I have my 5 points there are 5 key points. I have these two up above, these two red ones down below, and my x-intercept in this case. And if I get a y-intercept, then that would also be a key point. So you can kind of see that here are my points that I would need to get the graph, and this is a good sketch of what the graph is going to look like. So in this next one, we're going to do the same thing. We're going to sketch the graph, and we're going to go ahead and try to figure out some information about it. So first thing I'm going to do is, well, let's go with x-intercepts. And just like I did before, so if I do x-intercepts, I'm putting y equals 0, and I get x over x squared minus x minus 2. And if I solve this, remember, this x on top is being divided, so I'm going to multiply both sides by the bottom here. And so then I get x squared minus x minus 2 times both sides, x squared minus x minus 2 times 0 is just 0. And so then I get x equals 0, so there's my x-intercept. So at my x-intercept, and it happens to be a y-intercept also in this case, because a 0, 0 crosses both of them. So I don't have to do the other one. So my x and y-intercept is 0, 0. Because I put 0 in for y, I get 0 for x, so that's where we're crossing. And so then, so 2 of my points are taken up. So then I'm going to go ahead and look for vertical asymptotes. And vertical asymptotes are always found when we set the bottom of the fraction equal to 0. So 0 will equal x squared minus x minus 2. And in order to find out what these are, I can't really add 2 across, and they're just not going to work that way. So I'm going to have to factor it. And so when I factor the bottom, I get x minus 2 times x plus 1. And so it looks like, using my zero product property, I can say x minus 2 equals 0 and x plus 1 equals 0. Using my zero product property here, I can solve for x, and I know that x can't equal 2 and x cannot equal -1. That's where our vertical asymptotes are. I'm saying cannot because they're not in the domain of the function, but they are the vertical asymptotes. So I will draw vertical asymptotes where those are. And so at -1, I have a vertical asymptote. It's a little hard to see on this background, but you can kind of look at it. And then you can see the other one over there. So there's my 2 vertical asymptotes. Let's see if we have a horizontal asymptote. And so for a horizontal asymptote, we're looking at the degrees of the function. And in this case, the degree of the top is bigger than, or is smaller than the degree on the bottom. So the degree of the numerator is 1 and the degree of the denominator is 2, which basically means that we have a horizontal asymptote at 0. So we're going to have our horizontal asymptote at y equals 0. And so if I draw my horizontal asymptote, it'll be at y equals 0. And so now you're probably saying, well, we have an x-intercept. We have an x-intercept at 0, 0. How can that work with a horizontal asymptote at 0? Well, horizontal asymptotes aren't necessarily like vertical asymptotes. Vertical asymptotes are the absolute. You cannot cross a vertical. You will not cross a vertical asymptote. A horizontal asymptote, on the other hand, is kind of the end behavior. What is happening to the graph as you go out to infinity? And so, yes, there are times where you might cross over a horizontal asymptote, and this is one of those cases. You can see I have a point that's right on the horizontal asymptote. But if I go out this way, if I go out to my infinity as x gets infinitely large or x gets infinitely small, excuse me, if x gets infinitely small, then basically what ends up happening here is that we're going to approach this horizontal asymptote. So we're going to take our key points here. We're going to set up a t-table and pick up some points and figure out what's going on with this graph. So I want to know whether this graph is going down or going up. So I'm going to pick two of my points in the middle there. So I'm going to pick x is negative a half and x is positive 1. I already know what 0 is, so I'm not going to bother with that one. That will give me the middle part. I'm going to do this side over here in blue, and so I'm going to pick numbers on the other side of the vertical asymptote, which would be something like x could be 3 and 4. That'd probably give me a good idea. And then I'll do the last one in black, and that would be picking in the negative sides, and I got to go less than -1, which would be -2, and say -3, and those should give me a pretty good idea where my graph is going. So if I start with the red one, if I put 1 into this function, I get 1 over 1 minus 1 minus 2, which means I end up with -1/2 for that. So at this point at 1, I'm down here at -1/2. It could be that this at -1/2, I could be down here, and this could be like an upside down parabola, or it could be up here in the positive, and it's going up. So I don't know how much I'm going to work to actually get the actual number, because I'm not really concerned about that. I really just want to know which way the graph is going, whether it's going to be in the positives or in the negatives. So I'm going to concern myself with whether the top or bottom is positive or negative. So putting in a -1/2 for x, the top is negative. And then the bottom of the fraction, by putting in a -1/2, when I square it, that becomes positive. When I put a negative into a negative, I get a, well, I'm going to actually have to figure out this number. There's no way for me to do it without. So then, if I put in a half, I get a -1/2 on top, and I'm going to have to write this out. I'm going to do it up here, because I don't, well, actually, let's see. I can probably do it down below. I got some room. -1/2 on top. Then I've got -1/2 squared minus a -1/2 minus 2. So I just plugged in -1/2 into the function, which now you got to be able to work with some fractions here. We get 1/4, which is positive, plus 1/2 minus 2. So on the bottom here, if I make this 2/4 to get a common denominator, I really have -1/2 over 3/4 minus 2, which if I take $2 away from 75 cents, I have -1/2 over 1 and 1 1/4, which is really 5/4. And so now at this point I have a positive on the top and a negative on the bottom. So this thing's going to be, oh, that should be a negative on the bottom because I took away 2. So I've got a negative top and bottom, so that means my number is going to be positive. And so since it's positive, it's got to be above the x-axis, so it's going to be somewhere up here. And so my graph is going to look like, kind of like a cubic, but it's going to go something like this. It's going to approach both vertical asymptotes. And you can figure out the exact number if we wanted. We have -1/2, and remember when we divide fractions, we multiply by the flip. And so you can see I end up with 4 over 10 as my number, which reduces to 2/5, which would be, it's positive 2/5 in there. And so that's kind of where my point is. And so that's how the graph, that's kind of a sketch of that graph. If I put 3 into this function, I get 3 over 9 minus 3, which is 6, minus 2. So I end up with 3 over 4. And it's just a matter, you can crunch the numbers on these if you want on your own. If I put 4 in, I get 4 on top, and then on the bottom it's 16 minus 4, which is 12. 12 minus 2 is 10, so I have 4/10, which is 2/5. 4/10, which is 2/5. So at 3, I'm at 3/4, which is almost 1. Right there. And at 4, I'm at 2/5, which is a little less than half. So I'm getting closer, so the graph should look something like this. Going to approach the vertical asymptote that way and the horizontal asymptote over there. Then I'm going to find out, now I need to find out which side of the horizontal asymptote I'm on over on this side. And so by putting in -2 into the function, I get -2 on top, 4 minus a -2, which is adding. So I really end up with -2 over, in this case, 4, which is a negative 1/2. So at negative 2, I'm at negative 1/2, so the graph is going to be down here. And I don't really even need the negative 3. I just know that I'm approaching the horizontal and the vertical asymptotes this way. And so that's the sketch of the graph. And since I only needed 5 points, I'm not going to go with the negative 3, but you could plug it in and figure out where that's going to be. It's probably going to be closer than 1/2. It might be the 2/5 or something, negative 2/5. It would be closer to the 0 horizontal asymptote. But as you can see with my horizontal asymptotes, this blue line, as x gets bigger and bigger, it's going to get closer and closer to the horizontal line but never cross it. Likewise, as x gets smaller and smaller, I'm never going to cross that horizontal asymptote. So then finally, we have this rectangular page that looks like this. It's designed to contain 48 square inches of print. So the printing is going to be on the inside here. And the margins on each side are 1.5 wide, and the top are 1 deep. And so what should the dimensions of the page to minimize the amount of paper that is used? So we want to include 48 square inches, but we also want to minimize this, so we want to, that's area. So we're going to have two equations. We have a perimeter equation, which would be the paper that's going to be used, and then we have an area equation which will maximize or minimize in this case. So the area equation that we're going to use is, we're going to say, well, my x value is x plus the 1.5 on each side for the total area, so it's going to be x plus 3 times, and then the y value would be y times y plus 2. So there is my area equation. Then I also know, actually, and I'm taking that back, it's not going to be a perimeter, it's going to be another area equation that we're going to use. The other area equation that we're going to use is the area of the print, which is what they told us. I got to kind of pay attention to what I was talking about earlier. And so I know the area of the print is 48 square inches, so that's x times y equals 48. And so if that's the case, then I need to solve for y to replace it so that I can do this all in terms of x, so that I could graph it. So my area, so if I solve for y in this blue area equation, y is going to equal 48 divided by x. So I'm going to plug in 48 divided by x in for y, and so then my new equation is going to look, my area equation for the whole paper is going to be x plus 3 times 48 over x plus 2. And so with this, I have to get, if I go ahead and get a common denominator, to put, well, I can get a common denominator on this side, which will make my life much easier. And so the area would be x plus 3 times 48 plus 2x all divided by x. And that, how I get this is I multiplied this x over here, this 2 by x over x to get a common denominator, and that's where this x came from. And so then I could write it as one big fraction. So then I'm going to multiply these guys together, and we're going to leave that denominator. So the area is going to be x plus 3 times 48 plus 2x all divided by x when I multiply them together. Since I'm multiplying, I don't have to get a common denominator. And if I want to minimize this, I need to find out what x is. So I can go ahead and do this on my graphing calculator. The key is that I needed this equation in order to find out where the maximum or minimum on the graph was. So I'm going to get the graphing calculator, and then we will. So with my graphing calculator, I went and graphed this function, and I'll show you the function that I graphed. I typed in x plus 3 times 48 plus 2x all divided by x, and I got this graph. All right, and so what happens here with this graph is that I am looking for, since the question was what is the minimum of this, then I'm looking for a low spot in the graph. And with that, I'm going to kind of I'll pull the picture out, but I'm going to go back to the graphing calculator in just a second. What happens is, as you can see with the graph, that it is going down, and then somewhere out here, it looks like it's going back up. So my minimum is going to be somewhere in this area, I'm guessing. And so to minimize, this will minimize the area of the paper that's going to be used. and keep the 48 square inches of paper of type that we want. And so that's really what we're trying to find. We need to find the dimensions of the x and the y that will do this for us. And so we're going to find the x value that will do this, and then that will give us the 48 square inches the best we can. So I'm going to go ahead and pull up my calculator, and this is where I do a minimum. So second, calculate, go to minimum, which is 3. So now I'm going to the left of the minimum, and I'm looking at my y values, okay, and then I'm going to go to the right. You see my y values are going back up, so and then I'm going to somewhere in the middle make a guess, and so I made a guess. So this is the minimum that I get, and it's kind of close to where I was before, and so I'm just going to kind of lay this on top if I can, and you can kind of see. Let's see if I do a little trickery here. I'm going to, oops, that's not what I wanted. Let's try this again. Kind of lighten up the one that I'm talking about here. You can kind of see that the blue spot is about where I was guessing it to be. And so that's really what I was looking for, is what is the minimum of this. And you can see that the x value to make this a minimum is going to be 8.49 inches. And so if that's what we're looking at, then we have to say, okay, that's the x value, but that's the width of the paper, and that's basically going to get me that value. But the problem is I want to know what the total value is, so I have to add on the 3 from the original, because we're looking for the actual size of paper. So I could say that the x for the whole paper would have to be about 11.5 inches wide to get the whole paper width. And so then if I want to go back and figure out what the y value is, then I can just go ahead, and since I know that x is 11.5, that equals y here, I can just go ahead and plug that in and solve for that, and that should give me a y value of approximately 7.6 inches. So we're going to get 11.5 by 7.6 inches would minimize the size of the paper that I'm going to use, and make sure I have 48 square inches in there without losing it. So this is the conclusion of all the examples in this section. If you have any questions, please remember to mark them down, or go back and mark them down, and come into class with questions. Thank you.